We'll learn about the half adder and the full adder circuits. And first, let us start with the half adder circuit. So this half adder is the combinational circuit which adds the two bits and it gives the sum and the carry bit as the output. So now let us see what is the logic circuit of this half adder. And for that, using the truth table, first of all let us understand that when we add the two bits, then what are the possible outcomes? So for the two bits, there are total 4 different combinations, right? So here, these 0 plus 0 is equal to 0. That means whenever these a and b is equal to 0, then the sum bit and the carry bit both are 0. Similarly, these 0 plus 1 is equal to 1. That means this sum is equal to 1 and the carry is equal to 0. Likewise, this 1 plus 0 is equal to 1. That means whenever this a is 1 and the b is 0, then the sum bit is equal to 1 and the carry bit is equal to 0. And likewise, this 1 plus 1 is equal to 0 with 1 as a carry. That means whenever both a and b is equal to 1, then this sum is equal to 0 and the carry bit is equal to 1. So this is the truth table of the half adder. So as you can see, this sum output is equal to 1 when a is 0 and b is 1, or when a is equal to 1 and b is equal to 0. So if you see the Boolean expression of the sum output, then it is equal to a bar dot b plus a dot b bar, or it is equal to a XOR b. Similarly, this carry bit is equal to 1 when both a and b is equal to 1. Therefore, if we see the Boolean expression of this carry bit, then it is equal to a dot b. So these are the Boolean expression of the sum and the carry. So now let us implement them using the logic gate. So as you can see these expressions, the sum output can be implemented using one 2 input XOR gate, while the carry output can be implemented using one 2 input AND gate. So this is the logic circuit of the half adder. Now this half adder circuit works perfectly when there is a no incoming carry. But if there is an incoming carry from the previous addition, then we cannot add that carry using this half adder. For example, let's say we want to add these two binary numbers. Now the LSBs of these two numbers can be added using the half adder because during the addition there is no carry. So after the addition, this sum bit is equal to 0 and the carry is equal to 1. So now in the next column if you see, then we have the carry bit along with these two bits. And this carry bit is generated from the previous addition. So if we try to do the addition using the half adder, then simply we need to ignore this carry bit. And that is the limitation of this half adder. That means using the half adder, we cannot add the carry which is generated from the previous addition. So if we want to do the addition of the two bits along with the carry bit, then it can be performed using the full adder circuit. So this full adder is the combinational circuit which adds the two bits and the incoming carry bit and generates the sum and the carry bit as the output. So now let us see the logic circuit of this full adder. And for that, first let us see the truth table of this full adder. So here for the 3 inputs, we have total 8 different combinations, right? So here in the first row, this 0 plus 0 plus 0 is equal to 0. That means the sum is equal to 0 and the carry bit is also equal to 0. Similarly in the next row, this 0 plus 0 is equal to 0 and then this 0 plus 1 is equal to 1. That means in the second row, the sum is equal to 1 and the carry bit is equal to 0. Then in the third row, this 0 plus 1 is equal to 1 and then 1 plus 0 is equal to 1. That means in the third row, the sum is equal to 1 and the carry bit is equal to 0. Likewise in the fourth row, this 0 plus 1 is equal to 1 and this 1 plus 1 is equal to 0 with 1 as a carry. That means in the fourth row, the sum bit is equal to 0 while the carry bit is equal to 1. Likewise, in the fifth row, this sum bit is equal to 1 while the carry bit is equal to 0. And similarly, in the sixth row, 1 plus 0 is equal to 1 and the 1 plus 1 is equal to 0 with 1 as a carry. That means the sum bit is equal to 0 while the carry bit is equal to 1. Similarly, if we see the 7th row, then in this row 1 plus 1 is equal to 0 with 1 as a carry, and then this 0 plus 0 is equal to 0. That means here the sum bit is equal to 0 while the carry bit is equal to 1. And finally, in the 8th row, 1 plus 1 is equal to 0 with 1 as a carry, and then this 0 plus 1 is equal to 1. That means in the 8th row, the sum bit is equal to 1 and the carry bit is also equal to 1. So in this way, we got our truth table for the full adder. So as you can see, this sum bit is equal to 1 for the 4 different input combinations, and likewise this carry bit is also equal to 1 for the 4 different input combinations. So now let us find the Boolean expression of the sum bit and the carry bit, and then let us try to minimize them. So as I said, this sum output is 1 for the 4 different input combinations, and this is the Boolean expression of the sum output. So now in the first two term, if we take this a bar common, then in the bracket we will have this b bar dot cin plus b dot cin bar, and that is equal to b XOR cin. Similarly, in the last two terms, if we take this a common, then in the bracket we will have this b bar dot cin bar plus b dot cin, and this is equal to b XNOR c, or that is equal to b XOR c whole bar. That means we can write this expression as a bar dot b XOR cin plus a dot b XOR cin whole bar. Now let's say this b XOR cin is equal to x. That means we can write this expression as a bar dot x plus a dot x bar, and that is equal to a XOR x, or we can say that it is equal to a XOR b XOR cin. So that is the simplified expression of the sum output. Similarly, let us find the minimal expression for the carry output. So as you can see from the truth table, the carry output is equal to 1 for the 4 different input combinations, and this is the expression of the carry output. So now we can find the minimal expression using the K-map, and for that, first of all let us write down all the minterms in the K-map. So here this a bar dot b dot cin corresponds to minterm m3. Similarly, this a dot b bar dot cin corresponds to minterm m5. Likewise, this a dot b dot cin bar corresponds to minterm m6, and this a dot b dot cin corresponds to minterm m7. So here we can make the group of these m5 and m7, and similarly we can also make the group of m6 and m7. And likewise, we can also make the group of this m3 and the m7. So here, this group corresponds to b dot cin. Similarly, this group in the yellow color corresponds to a dot b, while this group in the blue color corresponds to a dot cin. So if you see the overall minimized expression for this carry output, then it is equal to a dot b plus b dot cin plus a dot cin. Apart from that, we can also write the C out in the different way. So in this expression, if you see the last two terms, then this a dot b is common. So let us take it outside. Similarly, in the first two terms, this cin is common. So if we take this cin outside, then in the bracket we will have a bar dot b plus a dot b bar, and it corresponds to a XOR b. Similarly, in this first term, this cin plus cin bar is equal to 1. That means we can write this expression as a dot b plus cin dot a XOR b. So that is the another way of writing the carry output. Well, why we have written this expression in this fashion, it will get clear to you very soon. But this is the second way of writing the output C out. Apart from that, this carry output can also be written as a dot b plus b dot cin plus a dot cin, and the sum output can be written as a XOR b XOR cin. So now based on this Boolean expression, let us see the logical circuit of this full adder. So first, this sum output is equal to A XOR B XOR Cin. So it can be implemented using the two XOR gates. So the output of the first XOR gate is equal to A XOR B, and it can be given as an input to the second XOR gate. And the second input to the second XOR gate is equal to Cin. So the output of the second XOR gate will be equal to A XOR B XOR Cin. Similarly, from this Boolean expression, the Cout can be implemented using the 3 AND gates and 1 OR gate. So this is the logic circuit of the full adder. Now if you see the second expression of the Cout, then it is equal to A dot B plus Cin dot A XOR B. Now if you see this portion of the circuit, then we are already generating this A XOR B. So using the part of this circuit also, we can generate this carry output. So this is the another way of generating the Cout. So here, the output of the first XOR gate is applied to the AND gate, and the second input to the AND gate is equal to Cin. That means the output of this AND gate is equal to A XOR B dot Cin. Now using the second AND gate, this A dot B is generated, and using this OR gate, the output of the two AND gate is logically ORed, and this is our output Cout. So this is the another way of generating the Cout. And here if you closely observe, then this XOR gate and the AND gate is nothing but the half adder. Similarly, this XOR gate and the AND gate forms the second half adder. So using the two half adder and one OR gate, we can generate this full adder. So let us see the same thing from little different perspective. So we know that the half adder consists of one XOR gate and one AND gate. So instead of representing it with the logical circuit, we will represent it with this half adder block. But just assume that inside it consists of one XOR gate and one AND gate. So if A and B is the input to the half adder, then the carry output is equal to A dot B, while the sum output is equal to A XOR B. Now the sum output is applied as an input to this second half adder, and the second input to this second half adder is equal to Cin. So the sum output of the second half adder is equal to A XOR B XOR Cin, and similar to the A dot B, the carry output is equal to Cin dot A XOR B. Now after the first half adder, we are already getting this A dot B. So using one OR gate, we can perform the logical OR operation of these Cout1 and the Cout2, and that is our carry output of this full adder. So in this way, using the two half adder and one OR gate, we can design the full adder circuit. Now the full adder circuit, which we have discussed over here, can add two 1-bit numbers along with the carry bit. But if we want to add two n-bit numbers, then we need to use n number of such full adder blocks. So in the upcoming videos, we will see the arrangement of that circuit, and we will learn that how to design the adder circuit which can add two n-bit numbers. But I hope in this video you understood what is half adder and the full adder circuit, and how to design the full adder circuit using the half adders. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.